Okay, so what we want to do in this video is derive the least squares estimate for a general linear model. Now there's more than one way of doing this. You could use calculus, but I'm going to use linear algebra to do that. So let's first of all recap what we're going to try and achieve, and then let's have a look at how we're going to derive this. So we've got some data. So we look at our data here. We're going to assume that we have basically our predictors and a single response variable. So this first row here is for the first observation. So we've got our y1 and then we've got x11, etc. This will be the first predictor, the second predictor, the rth predictor. So our model is going to be this. It's going to be y equals beta 0, which is the intercept, plus beta 1 times xi1, etc., plus some noise term. And we're going to assume our standard noise. So it's IID, normal, mean of 0, variance of sigma squared. So we can take all this information and we can write it as vectors. So first of all, I'm going to have a column vector of the responses, which I'm going to denote as y. I've got our design matrix here. So the first column is the intercept. This is all the first predictor, second predictor, all the way to the rth predictor. We've got a vector of coefficients, and then we've got our noise vector. And so this now can be written as y equals x beta plus epsilon, the standard linear model. And basically, if the columns of x are linear independent, then the least squares estimate of beta is this thing here. Beta hat equals x transpose x to the minus 1 x transpose y. So y is a good thing because why is this true? Well, let's prove it. So what do we mean by least squares? Well, we're going to denote that as Q for beta. So we're going to change our B to minimize it. And what we're trying to minimize, the summation as I goes from 1 to n. And it's going to be yi minus, well, our model, beta 0 plus beta 1 x I1 plus dot 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 plus beta r x I r. I'm going to take this whole thing and we're going to square it. So basically we're going to go consider all the possible values of the beta r's. There's r plus one of them. Choose the one that makes this as small as possible. Well, we can write this in terms of the norm. This is going to be our vector y minus x beta. The underline obviously is that these are vectors squared. So it's the norm squared. No problem. How are we going to do this? Well, we're going to do the standard tricks. We're going to add 0. We're then going to take this term and we're going to complete the squares in terms of vectors. We're going to get the cross product to disappear, and then we'll use that to prove that you can't do better than that least squares estimate that we gave before. Okay, so let's start it step by step. So we've got our y minus x beta squared. And I'm going to write this as y minus x beta hat, where beta hat is the thing in the theorem, plus x beta hat minus x beta. So these are all vectors squared. So all I've done is I've added 0. This whole term here is actually 0. We've done plus 0. So we can write this as y minus x beta hat squared plus x beta hat minus x beta squared plus 2 y minus x beta hat transpose x beta hat minus x beta. So to some extent this is just the linear algebra equivalent of completing the squares. You've done it, if this had been, a plus b all squared, you'd have no problem. This is the linear algebra version. And what I'd like to do is I'd like to show that this is 0. So let's do that. Let's focus on that. So we've got y minus x beta hat transpose x beta hat minus x beta. So we're going to substitute in here and say this is y. Oh, I better underline all these like that. So we've got y minus x. What is beta hat? It is x transpose x to the minus 1 x transpose y. And this whole thing is transposed. And this term we can write as x beta hat minus beta. I'm not going to simplify that more than that at this point. So let's take out the y here. So I've got I minus x, x transpose x minus 1 x transpose, all by y transpose x beta hat minus beta. Now, let's have a quick aside. If I have two matrices A, B, and I transpose them, that is equal to B transpose A transpose. So using this little fact, we can rewrite this as Y transpose I minus X, X transpose X minus 1 X transpose. So this here is my A and this here is my B. Oh, that's a nice straight line. That's not normally like me. And then we've got X beta hat minus beta. Okay, so next, A plus B transpose is A transpose plus B transpose. So I can transpose this and I can transpose this. But this is complicated. I've got X transpose X to the minus 1 X transpose. Well, let's think about this. This is A, B, C transpose, which is, oh, I've got to get this right, C transpose, B transpose, A transpose. So this is going to be X transpose transpose, X transpose X minus 1 transpose X transpose. This is symmetric. We can interchange these two, and the whole thing, it's just lovely. You take that and you just get the same thing back. You get X transpose X minus 1 X transpose. The whole thing is symmetric. If you transpose it, you just get back what you started with. So let's take this, and what we have is we have Y transpose. We have I minus, because again I is symmetric, so I transpose is I. X transpose X to the minus 1 X transpose. So we've got that. We've then got the term X, and then we've got the term beta hat minus beta. Before we go on, John is going to just check and make sure he hasn't made any major mistakes. He hasn't. Booyah. Right, so this is Y transpose. And I'm going to multiply on the right by this X. So I've got X minus X, X transpose X minus 1 X transpose X, beta hat minus beta. Well, X transpose X minus 1 X transpose X must be just I. So this whole thing is Y transpose X minus X, beta hat minus beta. This is 0, so the whole thing is 0. Lovely. So that cross product, as we guessed, would be 0. So what does that mean? It means that the sum of squares, the arbitrary sum of squares, x minus beta squared, is going to be the sum of squares I would use if I use my x transpose to the minus 1 x squared plus another term x beta hat minus x beta squared. This is greater than or equal to 0. So this here, we have that for any arbitrary sum of squares, it will always be greater than or equal to the sum of squares I would get if I used our beta hat. Or in other words, you can't do better than this. This is the least squares estimate. In fact, you say, well, when do you actually get that? When do you get equality? You get equality when this thing is equal to 0, and this will only be equal to 0 if beta equals beta hat. There you are. That's it. You could do a matrix calculus as well. I quite like the linear algebra. It's what I was first shown. It's what I'm used to. It's great. It's a lovely little bit of the simple tricks that you see throughout your stats career, just used again. Add 0, expand, get rid of the cross product. Booyah. Excellent. All done. Thank you very much, and I'll see you next time.